All right, so now we know the setup of partial fractions. We know the why we want to use partial fractions. Let's get to actually figuring one out together. So we have the integral of 4x squared plus 13x minus 9 over x cubed plus 2x squared minus 3x. So we know first thing we have to do is we have to factor that denominator. Okay. All right, so let's see, let's factor out an x. And nope, that's a minus 3. Okay, now looking at this, x squared plus 2x minus 3, that's x plus 3, x minus 1. All right, we have it factored. Okay, so now what we have to do is we have to split it up into the different fractions with our different denominators. So this is going to be equal to, all right, so the way I want to set this up is we're going to drop the integral signs and we're just going to set these two functions equal to each other. So I'm going to say 4x squared plus 13x minus 9 over x plus 3 x minus 1. And I didn't mean to set these two equal to each other. I want to set this one equal to our partial fraction decomposition. Now, because we have 3 factors in the denominator, we have 3 different fractions that we're going to use. Now, our first denominator has to have x. X is a linear term, so it gets a constant numerator. Our next factor in the denominator is x plus 3. That is also linear. It gets a constant numerator. X minus 1 is our last, and that is also linear, so it gets a constant denominator. So I set the original equal to my decomposition where I have these 3 constants a, b, and c. Now we have to solve for a, b, and c. Now this is going to be a combination of kind of using systems and some other little tricks that we can use here. But when I look at this equation, I don't like the denominators. So what we are going to do is we're going to multiply everything by this denominator, the LC, which is actually the LCD of all 4 of the denominators. So we're going to multiply by x, x plus 3, x minus 1. Now when we take this times our first fraction, this is equal to that denominator, so they cancel, leaving us with 4x squared plus 13x minus 9. Now when we distribute it to this term, we would have an a, the x's cancel, then we have x plus 3, x minus 1, plus, now distribute to this term, we have a b, the x plus 3's cancel, and we still have the x minus 1 left from the LCD, plus c time, now the x minus 1's cancel, c times x, x plus 3. So here's this equation, no more denominators. Now, there's a kind of a couple techniques that we're going to use, but the first one I want to use is a little trick here to simplify things quite a bit. Here's what I notice. I notice that this term and that term both have an x in there. And what happens if that x were a 0? Well, this whole term would be gone, and that whole term would be gone. Now, what happens if I put 0 in for these x's? Is that whole term gone? No, it's not. It's a times 3 times negative 1. That term still is, it's alive. It's still there. Okay. How about if I put zeros in for those x's? Okay. We have just a negative 9. So let's let x equals 0, and let's see what equation we get. We get negative 9 equals a times 3 times negative 1, which is negative 3, plus that 0, plus that 0, and we're left with this. So right away, we get a equals 3. Okay, so that's a nice little trick. Is there a value of x that you could substitute in that gets you just one of your unknowns left in the equation? All right, that looks good. Now I wonder if I can use that trick again to get another unknown. Well, when I look at this term and that term, they both have an x plus 3. So what if I let x be negative 3? Then this term is gone. And if I let x be negative 3, oops, right there, that term's gone. This term, would it be gone if we let x equal negative 3? No, it wouldn't. So let's use that one. Let's let x equal negative 3. Now, what do we get on this side? I'm going to have to grab my calculator. I'm not going to draw all like these zeros I did with the orange. But we're substituting negative 3 in for x. So 4 times negative 3 squared plus 13 times negative 3 minus 9 gives me negative 12 equals. Now the negative 3 for this term makes it all go away. How about the negative 3 for this one? B times, what do we have? Negative 3. I'm just going to write this out so I don't goof it up. Times negative 3 minus 1. Now this term is gone. So we have negative 12 equals, this is negative 3 times negative 4, which is 12. So negative 12 equals 12b. And we have b equals negative 1. Okay, excellent. Now we only have one more unknown to find, and that would be c. Okay, now as you guys watch these videos, it's important that you're trying to think ahead. You're trying to think, okay, what's he going to do next? So if you haven't done so already, just take a couple seconds and look and see, what could you do to find c? Hopefully you've spotted that both of these terms have an x minus 1 in them. So if we were to let x equal 1, those terms are going to disappear. If x equals 1, we still have our c, and we're still over here. So let's let x equal 1. What does that give us? Well, that'd be 4 plus 13 minus 9. 17 minus 9 is 8. That term's gone. That term's gone. And if x is 1 here, we have c times 1 times 4. C times 4. We get c equals 2. So we have our a, our b, and our c. So what we can do now is we can take our original integral and we can set it equal to the integral of a over x. What was our a? 3. 3 over x. Plus b over x plus 3. What did we solve for b? b is negative 1. Negative 1 over x plus 3. Lastly, we had c over x minus 1. That's going to be 2 over x minus 1. Now, let's find the antiderivative of these. This one is just 3 times the natural log of the absolute value of x. This is minus the natural log of the absolute value of x plus 3. And this is 2 natural log of the absolute value of x minus 1. Notice all of these, the derivative of the inside is 1, so we don't have to worry about doing a substitution chain rule kind of stuff. There we go. All right, let's look at another one. This one might take us a little bit longer, so this might carry over into another follow-up video from this one. Here we go. We have a cubic in the numerator. We have a linear term times a cubic in the denominator. So our degree of the numerator is 3, the degree of the denominator is 4. So let's see if we can't do our partial fraction decomposition. It's already factored for you. I didn't have to make us work it all for that one on this one. So let's set the original. Let's drop the integral sign just to set up our partial fraction decomposition. And let's set this equal to, okay, how many fractions are we going to have? Well, we have to have an x plus 1 in the denominator for our first. That's a linear term. It gets a constant numerator. Plus, now we have a linear term again of x minus 2. Okay, it gets a constant term. Plus, Now this is repeated 3 times, and if you recall from our last video, if we repeat something, we have to kind of build up those powers until we get it to be the third. So we're going to put an x minus 2 squared. The factor is still linear, so this is still constant. And then we do an x minus 3, x minus 2 to the third, which is still a linear term. Its numerator is still constant. So now this is what we've got. And like the last one, we're going to want to multiply by the LCD, which is x plus 1, x minus 2 cubed. When we multiply that to the left side of the equation, the denominator is canceled out. We have 3x cubed minus 18x squared plus 29x minus 4. Now let's multiply it into this. We have an a, x plus 1's cancel. We have x minus 2 cubed plus b times. Now one of the x minus 2's are going to cancel, leaving 2 of them, and we still have the x plus 1. C times, well, we'd have the x plus 1. Now 2 of those are going to cancel with an x minus 2, and I'm just running out of space. And then we're going to have a, I'm sorry, I'm just going to write it down here, d times x plus 1 for the last term. All right, so now what about that trick that we learned from the last problem? Is there a value of x that can reduce our 4 unknowns of a, b, c, and d maybe down to 1? Okay. And take a look at this for a moment. Is there something that could do that? Well, when you look at the factors, I see an x plus 1 in all 3 of these. So if we let x equal negative 1, these 3 terms are all gone. This one would remain. Okay, so let's let x equal negative 1. So what do we get from that? Let's substitute negative 1 in for every x value. 3 times negative 1 cubed minus 18 times negative 1 squared plus 29 times negative 1 minus 4. Negative 54 equals a times, well, when we put negative 1 in here, we have negative 1 minus 2, which is negative 3. Negative 3 cubed is negative 27. And like we said, all 3 of those terms would be 0. So from this, we get a equals 2. Okay. Now let's try to go on to another unknown. And I say, okay, well, I can make the a go away if I let x equal 2. Okay. If we let x equals 2, that's going to be 0. That's going to be 0. That's going to be 0. But our d term will still be remaining. So let's let x equal 2. All right, I'm going to do that on my calculator here. Left side, I get 6. On the right side, 0, 0, 0. D times, what are we letting x equal 2? D times 3, so we get d is 2. All right. Now, how about the last two? Okay. Well, how do I get this b term left? Well, I can't let b equal negative 1. I can't let x equal negative 1 or x equal 2. We've done that, and the b and the c terms have both disappeared. There's nothing I can substitute in that will make the a, the c, and the d disappear, but the b still be alive. So we're going to have to look at another option to do that. It's going to take a little bit of grunt work, but it actually works out pretty well. So I'm going to wrap up this video now. In the next video, you'll see me continue on with this problem.